Let's take a quick walk through chapter 15 equations. In this chapter, we're talking about alternating current, electricity, both voltage and current, and this is this is what we use in standard power distribution in the United States and most of the world. You can use direct current, but there are advantages to the alternating current. One of them being it's a little easier to transmit over long distances. So here's the basics of this. The voltage is going to vary as a sine wave, sine omega t. Omega is your angular frequency. The current is going to vary as a sine wave. The ratio between voltage and current, well, in Ohm's law for a resistor, that's just the resistance. When we start talking about capacitors and inductors, when you're in a DC world, an inductor is a short, a capacitor is an open. But when you're in an alternating current world, they have their own reactance in the circuit. The capacitor's reactance is 1 over omega C, right? We call it reactance XC. The inductor's reactance is omega L, so you can see they're very different from each other. 1 over omega C versus omega L. We define a few quantities. The root mean square voltage. So if you know your peak voltage, the RMS voltage is just your peak voltage divided by the square root of 2. Now this is important when you start talking about your household power. Household power, the RMS voltage is around 110, 120. If you want to know the peak voltage, you got to multiply that by the square root of 2 to get there. When you have inductance or capacitance in a circuit, this introduces a phase angle between the current and the voltage, right? The current and the voltage are no longer completely in phase. If you look at them across a resistor, they're completely in phase, but if a circuit has some reactance in it other than the resistor, it gets out of phase. And this phase angle is given by the inverse tangent of the inductor reactance minus capacitor reactance over R. The AC versions of Ohm's law is I naught is V naught over Z, right? Where Z is your impedance, and the impedance of a circuit that has some capacitance and reactance in it is given by this simple equation, R squared plus XL minus XC squared. All of that, take the square root. Average of power associated with a circuit is 1/2 I naught V naught cosine phi. Now you can see this is why we try and minimize this angle phi and actually try and get it to 0 in most circuits because it shows up here in the power, and so you're not delivering power as efficiently if you have net reactance in the circuit. Power dissipated by a resistor, 1/2 I naught V naught, which is just the RMS current and voltage, right? It's nothing different there. Resonant frequency for an LC circuit, we covered that in the last chapter. Oh, pardon me. And the last bit, transformer equations, right? Quality factor for circuit, omega naught over delta omega. So, and our LC circuit has this omega prime, which differs from this by 1 over LC minus R over 2L squared. And so there's a quality factor for circuits that have some reactance and resistance in them. And you can express that differently in terms of omega naught L over R. A transformer. So a transformer takes advantage of the fact that the magnetic flux, so let's say I've got a coil of wire here, and then I come in and I put another coil of wire that is wound in the same physical space as the first coil of wire. That means they share magnetic flux, right? So the magnetic field going through there is going to be the same. And what happens is, even though these two circuits may not be connected at all, because of the magnetic flux and the mutual inductance, you end up with voltage on what's called the secondary due to current and voltage on the primary. And all this defines is the voltage on the secondary divided by the voltage on the primary is just the number of windings on the secondary divided by the number of windings on the primary. If you look at it from a current perspective, I would write this IS over IP, right, is NP over NS. So for the current, it's the inverse of what it is for the voltage, right? So these are transformers we use in everyday life. There's probably one somewhere near your house. The line voltage out at the street will be 1800 volts or so, and before you bring that into the house, you need to step it down to 220, 240, or 110, 120, somewhere in that range. And so we use transformers to take line voltage, which is much higher voltage, and step it down to something that's a little safer to use than 1800 volts. If you had 1800 volts in your house, it'd be a bit of a problem. And that's it for a quick review of the equations for chapter 15.